Got a chemistry test just around the corner? Well, you are in exactly the right place. Today, we're doing a super fast, super clear revision session on everything you absolutely need to know about acids and bases.
Okay, let's just dive right in. We're going to slice through all the confusing stuff and focus only on the core ideas that are going to get you those top marks. Think of this as your personal cheat sheet, ready to go.
So, first things first, what actually makes something an acid? It sounds like a simple question, but trust me, this one definition is the key to unlocking everything else we're going to talk about.
And here it is, this secret ingredient. For something to act like an acid, it has to be dissolved in water. That's the magic. When it's in water, it releases these positively charged hydrogen ions. You'll see them written as H+. Without water, something like hydrogen chloride is, well, it's just a gas. But add water and boom, you get hydrochloric acid because it starts pumping out those all-important H+ ions.
And what's so cool is that all of these properties link directly back to those little H+ ions. That sour taste from a lemon? Yep, that's citric acid doing its thing. The reason acidic solutions can conduct electricity, it's because those H+ ions are free-moving and can carry an electric charge. And of course, the classic lab test, turning blue litmus paper red. That's your #1 signal that you are dealing with an acid.
All right, let's get into the fun stuff, the reactions. First up, what happens when you mix an acid with a reactive metal? Now, the rule here is super simple, and it is always the same. You get a salt, and you get hydrogen gas. Every time. So here's a perfect example. We've got sulfuric acid reacting with zinc. And look what it makes. Zinc sulfate, that's our salt, and hydrogen gas. So how do we know for sure it's hydrogen? This is the classic test. You take a lit splint, put it at the mouth of your test tube, and you'll hear this really satisfying pop sound as the gas goes out. That's the telltale sign of hydrogen.
Next up, we have the reaction with the metal carbonate. This one's got a few more players in the game. When an acid meets a carbonate, you actually get 3 products, a salt, water, and you guessed it, a gas, carbon dioxide.
The real giveaway for this reaction is the fizzing that you'll see. That's all the carbon dioxide gas bubbling away, and the test for it is foolproof. You just bubble that gas through some lime water. If the lime water turns all milky and cloudy, you can be 100% certain you've just made carbon dioxide.
Okay, so we're clear on what an acid is. But here's the thing, not all acids are created equal. Some are incredibly powerful, the kind you see in movies, while others are much, much milder. This is all about the difference between strong and weak acids.
So what is the real difference? This is a super common exam question, so let's get this crystal clear. It has nothing to do with how concentrated the acid is. It's all about what's happening on a molecular level.
The big difference comes down to one word, ionization. A strong acid, like hydrochloric acid, completely falls apart in water. It unleashes all of its hydrogen ions at once. But a weak acid, like the ethanoic acid you find in vinegar, is a bit more reluctant. It only partially ionizes, meaning most of its molecules stay together, which results in a much lower concentration of H+ ions floating around in the solution.
Oh, right. We have totally nailed acids. So now, let's flip the script and look at their chemical opposites, bases and alkalis. They're definitely related, but there's a really important distinction you need to know.
So the definition of a base is actually pretty broad. Basically, if you see a compound that's a metal joined with either an oxide or a hydroxide, you're looking at a base. Think copper oxide or iron hydroxide.
Okay, but here's a super important detail that trips a lot of people up. An alkali is just a special type of base. It's a base that can actually dissolve in water. And when it dissolves, it releases hydroxide ions, or OH-. So remember this phrase, it's a game changer. All alkalis are bases, but not all bases are alkalis. And why? Because not all bases can dissolve in water.
So what happens when you mix an acid, which is full of H+ ions, with an alkali, which is full of OH- ions? Well, you get this awesome reaction called neutralization, and we can track it all using something called the pH scale.
This right here, this is the main event. The hydrogen ion from the acid and the hydroxide ion from the alkali, they're like magnets. They find each other, they combine, and poof, they form a totally neutral water molecule. And sure, there are other ions hanging around that make a salt, but this simple ionic equation shows you the real heart of what's going on in any neutralization reaction.
And that brings us to the famous pH scale, which is basically our roadmap to acidity. Think of it like a rainbow. Down at pH 1 or 2, you've got your super strong acids, and they'll turn universal indicator a bright, fiery red. Weak acids hang out in the orange and yellow zone. A pH of exactly 7, that's perfectly neutral and shows up as green. Then as we cross over into alkalis, the weak ones are blue and the really powerful, strong alkalis are a deep, rich purple, all the way up at pH 14.
Okay, for our final section, we're going to do a quick fire round on oxides. Getting your head around these will really complete your understanding. It's the bonus round.
This table breaks it all down perfectly. There are 4 types to remember. So nonmetals, they usually form acidic oxides, like carbon dioxide. Metals, they tend to form basic oxides, like copper oxide. Then you have the special ones, amphoteric oxides. These guys are flexible. They can react with both acids and bases. Zinc oxide is the classic example. And finally, you have your neutral oxides, like good old water, which just don't react with either.
And remember, these rules don't just exist in a textbook or a lab. From the pH of the soil in our gardens to the acid in our own stomachs, these chemical principles are happening all around us all the time. So now that you know the chemistry, where else can you spot it in action? That's all for this explainer. Good luck with your revision.